All right, guys. Miss Middleton here. We are going to zoom through the characteristics of a star as well as their formation. So buckle up. Here we go. First up, stars were the first guides for navigation. You know this. If you didn't know it, you knew it once you watched Moana. Okay. Stars are in the night sky. They move in a predictable way. You can see here they rotate throughout the night. But you knowing that can figure out where you're going. As long as you find the North Star, which is right there, you can figure out where you're going. The closest star to Earth is the sun, which I know might seem super obvious, but we've had kids on tests before who just completely forget that the sun is a star. All right, and it's our closest star. It's our star. What I need you to do is underneath the intro for stars, I need you to add this information. Constellations are groups of stars that make an apparent pattern in the sky. And the cool thing about these images right here is that it's showing you that, yes, it looks like they're all at the same distance, but if you would actually step back, and when I mean step back, I mean like 225 light years back, okay? You would be able to see that the stars are at different distances. Some are really far away at 225 light years away. Some are a little bit closer at like 125 light years away. But either way, these stars are at different distances, and it's the apparent pattern in the sky. This is Orion's belt, so this is the Orion constellation, okay? The night sky appears as a 2D projection, but there is light years between these stars, okay? Make sure you add this information into your notes. If you need to pause, do it. Onward. All right, a star is a large, hot, glowing ball of gas that is powered by nuclear fusion. It is not actually fire. I can't tell you how many students I've had in the past who are like, oh, well, what if I threw water on it, Miss Middleton? Well, it's not the same, okay? It's not fire. It's gas that is fusing inside. All right, and we'll talk about how that works a little bit later. Fun facts, there's about 9,000 stars visible to the naked eye. You would be able to see those 9,000 stars if you went to an excellent dark sky site. And I think in northern Pennsylvania, we have the largest dark park. I want to say it's like Dark Park in PA. Cherry Springs State Park. This is what the actual night sky looks like there. You're not allowed to have any lights on, and it's far away from other cities and stuff. There's considered like no light pollution. So you get this, you can actually see the Milky Way. It looks like spilled milk. That's why they call it the Milky Way, because there's no light pollution there. So Mr. Middleton and I are actually planning on going to this park, Cherry Springs State Park, this summer, hoping to see this because it's stunning. All right, anyway, so let me get back to this. Right now, if you live on a farm, you might be able to see some stuff here. I would say I live in suburban or urban transition, so I'm not seeing a ton of stars. And in the inner city sky, you see like 4 stars, which is sad, but you need light to see at night, okay? All right, so there's the Milky Way. What you were seeing in that one image at Cherry Springs, that Cherry Spring Dark Park, is you were seeing it from the side view, okay? Not from up above. So this is what we think it looks like from up above, the Milky Way anyway. And it contains approximately 200 billion stars, which again, whoa. The second largest star, or second closest star to us, is Proxima Centauri. It's 24 trillion miles away. which is about 4.2 light years. So you might be like, all right, yeah, 4.2 light years, that's not that bad. If you got onto a rocket and were moving at the speed of light, it would still take you 4 years to get to our closest star, besides the sun. That's crazy. Okay, so I'm just going to reiterate, and you already have this in your notes. Space is big, very big. So we use a measurement called a light year, which is approximately 6 trillion miles. Remember, a light year is not an actual time, it's a distance, and it's 6 trillion miles. It's the distance light can travel in 1 year, which is 186,000 miles per second, which is crazy. It's crazy. All right. How do we put stars into different groupings? All right. How do we, what are the characteristics of stars? Well, it's all related to the star's stage of life and its mass. And we're going to talk about that a little bit later. But the first thing here is color. You can see from this image that different stars can be different colors, which is pretty cool. Here you'll notice that blue is actually the hottest color. Science and art are kind of the opposite, where your art teacher might be like, use cool colors, and you're like, oh yeah, purples and blues are cool colors. In science, it's the opposite. Blue is hot, red is cold. Okay, and you might have remembered that from when you used a Bunsen burner, the inside of the flame, the little blue flame on your Bunsen burner is the hottest part. Or if you roast marshmallows and in a campfire you like to burn your marshmallows, so you put it in the blue part of the flame. Okay, what you're seeing down here is the surface temperatures of stars, the range there. And the coolest at 3000 Kelvin still melt your face off. But down here, where it's cooler, it's going to be red. Really, really hot ones are going to be blue. There isn't green, there isn't purple. I'm not sure why, but those just aren't normal colors for stars. The color is determined by the temperature, and we put them into spectral classes because of that. So you see these like O, B, A, F, G, K, M. You don't need to memorize that or anything, but you need to know that stars are classified by their color, which is related to their temperature. The hottest is blue, white, yellow, orange, red is the coolest. All right, and this is just another way that we show how we organize them. You'll see this diagram later. It's called the Hertzsprung-Russell diagram. And the red, as you see, is the coolest, and the blue is the hottest. All right. Next up, another way that we classify or characterize stars is by their size. And that depends on the starting mass of the nebula. So a nebula is gas and dust that it's kind of like a space cloud hanging out in space. And stars form there, and the bigger the nebula is, the bigger the star will be. The smaller the nebula, the smaller the star will be. So this ranges from supergiant or giant to average to dwarf. So dwarf stars are the smallest. Obviously, supergiants are the biggest. You can see in this image down here, the sun is very, very small compared to Arcturus. Yeah. It's pretty intense. We're going to watch this video really quickly, not the whole thing, but enough to show you the differences between the sizes of some of these things out in space. Maybe. Come on. We're going to zoom in a little bit. All right. So here's the moon. It starts with the moon. And then you see Pluto is actually smaller than the moon. Ceres is another dwarf planet that's smaller than Pluto. Then next up we have Mercury, Ganymede, which is Jupiter's moon, Mars, Venus, which is considered Earth's sister planet, Kepler's. This is one of the biggest rocky planets we've ever found. And then you have Neptune. This is our smallest gas giant that we have. Uranus, take note of its sideways rings. Then Saturn. And then here we have a red dwarf, and this is one of the smallest possible stars you can have. Jupiter, it's our biggest gas giant. And then one of the biggest possible planets is this weird named one that I'm not even going to try and say. Here's the sun. We are in a yellow dwarf star. And then there's Sirius, which is a main sequence blue star. Pollux is an orange giant. Arcturus is another orange giant. You have Aldebaran. They just keep on getting bigger. And these stars looks like they'll turn into a red giant, which right here is a supergiant. So you'll notice as they turn into supergiants, they turn red. So it actually cools down. All right. Hypergiants. We got some big ones here. Okay. Which is crazy, but interesting. All right. So size is another way we can look at these characteristics. All right, last one. The brightness of a star is going to depend on its size and its temperature. The apparent brightness is the brightness as seen from Earth. So distance is a factor. Obviously, the brightest star that appears in our sky is the sun because it's closest. But it's actually not the brightest star out there. We have a yellow dwarf star, okay? The absolute brightness is what we actually look at for like a number value of, oh, this one's definitely brighter than this one. And this is the actual brightness if all the stars were the same distance from Earth. So if we could pull all the other stars in line with the sun, we could actually look and say, all right, this one's brighter than this one. We could give an actual number value to it. All right, now we're going to talk about how stars form. And I'm going to just say again, a star's life depends on its mass, and its mass comes from how big its nebula is. So what you'll notice is there's two different cycles, life cycles that a star can go through. One is if you have like an average or a small sized star, this is like our sun, okay? And then a massive star is right there. And our sun is actually considered an average star, even though it's like in the yellow dwarf category, if you saw from that video. But we consider it average because we compare all our other stars to our star, obviously. All right, massive star, you'll notice it's a little more explosive. You have two options, end options. We're just going to talk about how stars form today. So they all start with a stellar nebula. It's a cloud of gas and dust where gravitational attraction causes the cloud to begin to collapse. So gas and dust, gravity starts working on it, and it starts to squish down. Okay, so that's right there, stellar nebula. How long a star lives depends on its mass, which remember, its mass is going to be determined by how much gas and dust is in this nebula. Next up would be the protostar stage. So it's being squished down, the nebula heats up, increases its density and pressure, okay? It's going to start glowing. So the protostar is going to be squishing down. It's going to start giving off light because it's getting hot, but it's not a real star yet. The protostar stage, just like a prototype, isn't the actual, like if you have a prototype for a car, you can't buy that prototype. It's not the real deal, okay? A protostar is the beginning stages. It's not the real deal yet. It's not a real star. It's just heating up. And then a star becomes a real star when extreme temperature causes the pressure and gravity to be great enough to start a fusion reaction. There has to be fusion happening inside. So fusion is when atoms of hydrogen join to form atoms of helium. So if you remember when we talked about the universe forming, the first element to form was hydrogen. And then gravity must have started working on those hydrogens, bringing them together, and boom, then we start having hydrogen join with hydrogen and make a whole new element, helium. So this is where elements come from, stars fusing. All right, let's watch this right quick.
Nebulous house, baby star.
Stars. There are young stars in these regions that are heating up gas clouds that surround them and making those gas clouds glow pink. Stars are made out of gas, basically, and our galaxy has gas. In fact, our galaxy, you can think of it as having an atmosphere of gas and dust that surrounds all of the stars that we see in the disk. And it's from this gas that new stars are born.
By observing nebulas at different stages in their evolution, the story of a star's birth begins to emerge. It all starts inside a cold, dark cloud of dust and hydrogen gas, where a quiet tug of war begins. The cloud wants to dissipate, like smoke in the air, but gravity wants to pull it together.
They're in a kind of balance between gravity pulling in and gas pressure pushing back out. Gravity wins, and the material crunches down into a disk that is the beginning of becoming a star.
As gravity pulls more and more gas towards the center of the disk, it gets denser and denser and hotter and hotter.
Fusion!
Until finally, at 18 million degrees, a miraculous transformation takes place. Hydrogen atoms fuse together to form helium, and with a burst of nuclear energy, a star begins to shine.
These stars eventually get their nuclear fires going in the core. And when they do, they heat up, they can expel the material that's around them so that it kind of clears up the neighborhood.
Over the next few million years, winds blow the surrounding gas into spectacular swirling patterns.
All right. No.
Nebula.
All right. So, really quickly, what is fusion? Nuclear fusion occurs in the sun's core. Hydrogen atoms combine to form helium, and it releases a huge amount of heat, radiation, and light. It takes over 10,000 years for the light to get from the sun's core to the sun's surface. So, fusion is happening. That energy has to travel through many layers until it gets out into space. Here we have gravity pushing in and fusion pushing out. It's a star is like a balloon, forces are balanced, so gravity is pushing in, and then you have pressure pushing out. That would be your fusion energy pushing back out. So a star's life is a balance of forces. Gravity is pulling in this force of attraction that pulls the star's matter, increasing its density, so it's pushing in. And then you have nuclear fusion pushing out, and heat caused by fusion creates internal pressure. So that fusion is going to put pressure out, pushing against that gravity. So it's this weird balance where gravity's constantly trying to kill it, but fusion is pushing back out. The last part that we're going to talk about is once a star forms, so once fusion begins, it's considered to be in the main sequence stage. All right, so 90% of the star's life cycle is in this phase. It's actively undergoing nuclear fusion of the element hydrogen, and gravity and pressure are balanced. Our sun is in this main sequence stage, all right? And it's constantly taking hydrogen and fusing it into helium. All right, and that is the end of your notes.